This video is part of a lecture from multivariable calculus, and I'm gonna talk about definition of double integrals. So let me start by giving you some recalls of one variable calculus and just a simple single integral. So we said that in one variable calculus, when we have a function y equals to f of x, then we say that the integral of fx dx from a to b is basically the area under the graph of y equals to f of x over the interval a and b. Okay, so it means what? It means that if we have x-axis, y-axis, and if we have a function f of x from a to b, this integral refers to the area that is under the graph. So basically the area under the graph of f from a to b. This definition is a definition geometrically. But when we want to calculate this, how do we do that? So to do the calculation, this is something that we did. So let me just basically graph the function. I'm gonna remove just these little parts. So we have y-axis, we have x-axis, and just assume that we have a function f of x like this, and then from a to b we want to basically calculate the integral. Something that we did is to basically partition ab into n subintervals. Okay, so the first step is to partition the interval AB into n subintervals like this. So we're gonna call A to be the first point x1, and then x0, and then we have x1, x2, to xn, which would be B. Okay, so we basically have just some partitions like this. Okay, for example, one of them is xi minus 1 and then xi. Okay, this is x0, this is xn. So we partition it into n subintervals, and then we say that basically xi minus 1, the length of any of the intervals, we're going to call it delta x, which is basically b minus a over n. So basically the length here would be delta x, which is b minus a divided by n, because we have n subintervals. Then step 3, we're going to choose a sample point that we're going to call it xi star in each of the intervals. For example, in the interval xi minus 1 and xi. Okay, so I'm gonna choose a sample point in here. I'm gonna call this sample point xi star. Okay, so now what is the idea here is that when we partition the interval into n subintervals, we're gonna make small parts like that. We're gonna make the interval between a and b, and basically the area under the graph, into some small parts. And then when we define a sample point, we consider f of the sample point to be basically the height for for example, this rectangle in here. Okay, so the height here would be f of xi star. Why is this helpful? It's just because I have the width and I have the height. So delta x times the height, which is f of xi, would be the area of this small rectangle in here. Just this word. Okay, now if we choose in each of the interval one sample point, and then we consider basically the height of the rectangle based on f of the sample point, we are gonna make little rectangles, and so we have just these rectangles based on the sample point that we're going to choose. And then the step 4, we're going to define that the integral from a to b of fx delta x would be what? Would be the summation of just little areas. So for example, the area for this yellow box in here, this yellow rectangle in here, would be the width delta x times the height. So delta x times the height, which is f of the sample point, and then we're gonna add them all up. So we're gonna add them up for each of these sub-intervals. And then if you notice that we might have some parts that we over-calculate, for example, this little part in here, and we have some parts that we didn't calculate, this little gap in here. But now if we have n goes to infinity, it means that we have small rectangles, then the approximation would be very good, because we basically are gonna cover these little parts that we overcalculate or we didn't calculate. That's why we take the limit of that as n goes to infinity, just to make very, very small rectangles and to calculate the whole area under the graph with a better approximation. So that's the whole procedure of Riemann sum. That's what we call it. And then there's a theorem that says that this definition is well defined if f is a continuous function. Continuous. Okay, now this is how we do the Riemann sum, and basically this is how that we define this this integral. But let me give you just a small note, and the note is that, you see, if we have the point is how we can calculate the sample point. What is the sample point? How to choose the sample point? It's basically arbitrary, but we usually, let me just graph the whole thing. I'm gonna copy this. I'm gonna paste it 2 times. Okay, and I'm gonna move this one a little up. Okay, and so you see, when we have a to b for each one of them, to b, a to b, if we choose in each of these intervals, if we choose the left point, for example, for any of the interval, we choose the left point, we're gonna make it like these intervals. So the sample point could be the left point. The sample point could be, you see, if we have this interval like that, it could be the right point. right point, and we consider the height of the right point in each of the intervals, and we can make it like the middle point. Okay, for the middle point, then we consider f of the middle point. I'm gonna make the middle point, and middle point has the better approximation considering all these right point, left point, and all other approximation. Middle point is usually the good one. Okay, so this is basically definition of the single integral. Now we're gonna do double integral. So I'm gonna say that similarly, double integral of a function of two variables, x and y, over a region R, and I'm gonna define the region R like that: all the x and y such that x is between a and b and y is between c and d. So I'm gonna basically define the double integral of f of x and y dA over the region R. What is A? Let me explain it. So in this situation, what we have z-axis. Let me try to graph it first. We have y-axis, and then we have x-axis, and so we have f, which is basically a surface, something like this. Oops. This is f of x and y. It is something like the surface, and then we want to calculate the double integral of that over a rectangle in here. So what I have, just wait a little so that I basically graph it. So we have AB, and then we have CD, and this is basically the area of my integration. This is the region R. Okay, and the double integral of f of x, y dA, A is basically element of the area, and this integral is basically the volume. It's the volume below the graph of f of xy over the region R on xy plane. Okay, so this double integral here is basically the volume of the solid that is below the graph of f over the region R. Okay, so this is definition of that geometrically. That's how we define the double integral, and it's good that we can calculate the volume of the solid using the double integral. It's very helpful, and the idea here is exactly similar to the idea that we have for the simple single integral. So for calculation, what we are gonna do, how to calculate the volume that we have in here. So as before, let me just give you an idea. As before, we have just we wanted to calculate the whole area under the graph, we just make it into small rectangles. Now we want to calculate the whole thing, the volume, so we just need to make it into small boxes, and then we just calculate the volume of each of the boxes, and then we add them up. In that case we get the volume of the whole solid. Okay, so step 1 is to cut the region R into small pieces of area that we call it delta A. Delta A with capital A. Delta A. And we just basically are going to do it like this. Okay? And each one of them, for example, this one in here, I'm going to call it delta A. Delta AI, let me call it, because we can have a name for each one of them. And if I want to just basically explain how we get that, we have x, y plane on here. We have AB, and then we have CD. Okay, so this is the region R, and we just made basically we make the region R into small pieces, and each piece is called a delta AI. Okay, and delta A is basically the area in here would be delta X times delta Y, right? So it would be delta X times delta Y, okay, because that's the element of the area. And what is delta X? Delta X is just basically this part. This is the width. Delta X would be B minus A divided by N, and delta Y is D minus C divided by, for example, M. If we make it into M pieces, N pieces in here, M pieces in here. Okay, that's how we get delta A. The step 2 is to, as before, we're gonna choose a sample point. Choose a sample point xi star yi star in delta A. Okay, so I just basically pick a point, like a sample point in here, xi star yi star, and then step 3 is to say that the volume of the box, the volume of the box above delta A, which is below the graph of F, is what? Is delta AI, okay, times what? Let me graph the volume. I'm gonna use this color. So see, I'm gonna go a little up like this, and then oops, no, don't change it, please. There you go. So I just have a small, as you see, just a small box, and the height of the box would be f of the sample point. Okay, so it would be the area of the base times the height. Okay, so delta xi, and then f of xi star yi star. Actually, why j star? Just because I and j would be different. Okay, And very good. And then step 4, actually since I and j are different, it's better, yeah, to have delta, for example. Delta AI would be good in that case. Okay, then we're gonna add them up. Add up all the volumes of small boxes. Okay, so this is the area of the base. This is the height for each of the boxes. And then, so we have a solid that we want to calculate its volume, and then we make it into small boxes. And for each box, we have delta A as the area of the base, and then we have a height. The height would be F of the sample point that we choose. Okay, exactly, kind of like similar that we did for the single variable case. And then we're gonna say that the volume would be approximately the sum of all of these boxes, Fi star, Yj star, delta A, I is from 1 to N, and J is from 1 to M, for example. Okay, and step 5 is to define like this. If we take the limit, we can have a better approximation. That's why we define the double integral of f of xy dA over the region R is the limit as m and n, both of them, goes to infinity. It means that we're gonna divide or partition each of these intervals into infinite pieces of the sum of I from 1 to n, j from 1 to m, f of xi star, yj star, delta A. Okay, and there's a theorem that says that if f is continuous function, continuous, then the double integral of f dA over the region R is well defined. Okay, very good. That's a definition of the simple integral. It's a bad color. Let me change it. Okay, this is better. How about the sample point? How can we choose the sample point? Let me just give you just one small note of the sample point. So the sample point could be the middle point in each of the area, which means basically the center of delta A. So for each of the boxes, the center, it could be the upper right corner. For example, if this is delta A, it could be this point, or it could be the lower left corner, which is basically for each of delta A, it could be like this. So that's why we have even different names for the Riemann sum. For example, calculating the Riemann sum for the double integral using the middle point, or using the upper right corner. Okay, I think we covered everything. Very good. And the next video, we're going to solve some examples.